Hey there, pre-calc. Welcome back to another series of videos here. This series is module 8.06, Graphing Polar Equations. Here we go. We got to continue to get mathematically literate in an uncertain world and an uncertain time. I applaud you all been submitting work online. You guys are continuing to submit work and watch these videos and ask questions. So I'm proud of you guys for continuing your education in the midst of such opposition and such weird, uncertain times. So here we go. We are graphing this equation, sine theta. R equals sine theta. We're not just graphing it like we used to graph. Here's a y equals sine x. Okay, the good old rectangular coordinates. That's what it looks like in rectangular coordinates. But what does it look like if we graph it on a polar grid? Okay, r equals sine theta. So I went ahead and printed some of this paper out again. If you go to the page where you found the link to this series of videos, I put this out as a PDF file for you to download if you want. Otherwise, just Google polar graph paper printable and you can print these out, no problem. Okay, so it might be helpful for this set of videos to have at least one or two of those printed out. Okay, we are going to graph r equals sine theta in polar coordinates. Now, last video I showed you how to graph things with your calculator, and yet again, your calculator and Desmos are going to do a much better job graphing these things than humans possibly can. But it's good to graph these things by hand just to get an idea of what's going on, so we have a better concept in our heads of what's going on. Okay, I put these things up here just as a reminder of what they look like on the graph, right? R equals 3. Well, that's a circle. R, remember, is the radius, the distance from the origin. So the distance from the origin equals 3. That would be all the points that are 3 units away from the origin making up that circle. Okay. Theta equals pi over 6. Well, that's the set of all points that have the orientation of pi over 6 from the positive x-axis. Okay, which is also called the polar axis, which is a new term that you might learn this unit. This is the polar axis right here, the positive x-axis. So all the points on pi over 6 would be the positive radius and negative radius points, so it would make up that straight line through the origin. So we can graph circles centered at the origin, and we can graph lines that go through the origin really easily in polar coordinates. That's one of the reasons that they're kind of nice. Okay. So I went ahead and labeled the angle values in radians, and for this activity you're going to want to make sure your calculator is in radians pretty much for this whole lesson. Yeah, for all of 8.06 you're going to want your calculator in radian mode. We rarely ever graph things on a polar degree graph. It's usually radians. Okay. All right, so the most basic way to graph equations is to make an input-output chart, fill it out, and plot points. It's the same in rectangular coordinates. It's the same in polar coordinates. We're going to just start calculating these, okay? So r equals sine theta. That's the equation we're graphing. We're not graphing these. That's just extra talking points, okay? So when theta is 0, well, what's the sine of 0? Well, that's 0, so r is 0, okay? When theta is pi over 6, well, what's the sine of pi over 6? If you have your unit circle, you can look at that, or maybe you just have these memorized by now. I hope you have at least some of the most basic one memorized. Sine of pi over 6 is 1/2. Okay, let's just do a few of these. Sine of pi over 4 is root 2 over 2, and let's approximate that with a decimal so it's easier to graph. Root 2 over 2, I think is 0.7, right? Yep, roughly 0.7. Sine of pi over 3 is going to be root 3 over 2, which is roughly 0.87. So we'll call that 0.9. We'll just round to the nearest tenth. And the sine of pi over 2 is 1. Okay, we'll stop and we'll graph those points. Okay, so I have a theta of 0 and a radius of 0. Okay. So what point is that on my polar grid? Well, just like with rectangular coordinates, 0, 0 is right there at the origin. I am 0 degrees from the x-axis, and I have a radius of 0 units away from the origin. So the origin, that point, is on my graph. Okay, pi over 6, 1/2. Pi over 6 is this angle. 1/2 would be right here, but I'm deciding right now that I don't want that to be a half. I want half to be much further out because we know that's the sine graph, right? Sine bounces between positive and negative 1. So y here will never be larger than 1 and never be less than -1. So I don't want this to be 1 because then my whole graph is going to be inside this tiny little circle here. So I'm going to change the scale of my graph, and I'm going to call this 1 right here. I'm going to say that's 1, so that means that, let's see, that's 1, 2, 3, 4, 5, 6 out, 6 grid marks out, so this will be 1/2. Okay, so I am at pi/6 is my angle, and I have a radius of 1/2, so that would be that point. Okay. Next one, pi/4 and 0.7. Okay, so pi/4 is along this angle, and 0.7. So there's a half. There would be 0.75. So 0.7 is probably like right there. Okay. And then pi/3, 0.9. Pi/3 is here. Well, there's 1, so 0.9 must be like right about there. Okay. And then there's 1. Pi/2, 1. So I've got 1, 2, 3, 4, 5 points graphed. And if we connect the dots, we have the first part of our graph. Okay, looks like it's maybe half of a circle. And if you guessed it was half of a circle, you'd be right. Okay, I am going to fill out the rest of this table just based on either my knowledge of the unit circle or using my calculator. And then I'll graph those points in 3, 2, 1. Okay, there we go. I have filled out the rest of my table and I have graphed. Well, let's see. I've graphed all the points in this half of my table. Okay, and I'll show you how we end up graphing these points. Okay, so I graphed all these points. Basically, we go past 2 pi/3, we get these points over here, and I connected all my dots, and we get this. Well, it's supposed to be a perfect circle. My graph isn't perfect because I didn't graph my points in exactly the right spot, but it's supposed to be a perfect circle there that is tangent to the x-axis. Okay, so remember, how do we deal with negative radii? Well, remember, we face our theta in the direction of that angle, 7 pi/6, so that's this direction, so we're facing this direction, but then we go a radius of -1/2, so we're facing that direction, and then we go backwards 1/2. Okay, so facing that direction backwards 1/2, that's going to hit this point. Okay, so it's just going to, the same thing happens here, 5 pi/4, we're facing this way, and then we go backwards 0.7, so we land on this point again. So you see that we're just going to cycle back through the same set of points that we've already graphed. So yep, for 2 pi, which is 1 revolution, we work our way around the circle twice. Okay, so I wonder if that was surprising to you. Maybe you didn't expect to get a circle that was tangent to the x-axis. I certainly didn't expect that the first time I graphed this. Okay, and it turns out that if we were to graph r equals cosine theta, what do you think you would get? Well, this time you get a circle that is tangent to the y-axis. Okay, that's the circle that you would get if you graphed r equals cosine theta. Okay, and I'm going to try to help you understand why you get a graph like this in polar coordinates where you had a graph like this before. Okay, and in order to do that, there's an applet that I'm going to show you here in a few moments, and I'm going to put a link to that applet. It's a GeoGebra applet you can find online, and we'll do that here in just a second. Okay, so here's that app that I was just talking about, and the link to this app is in the description right below this video. So I highly recommend you click on that and you start to play around with this to get a good idea of how these two graphs are related, how we relate a Cartesian graph to a polar graph, and why we get the shapes we do. Like, why did we just get this circle when we were graphing sine? And if you play with this, I think it's pretty clear. I'll try to explain this as I go along here. So here's our good old graph of sine, right? Starts at 0, increases, then decreases, and back to 0. And I think that most of you will remember that animation I showed you of that point going around the circle, and the height of that point as it goes around the circle, that's the y value, and that increases and then decreases, and that's the sine of the angle. And as the x value of that point increases and decreases, that's the cosine of the angle. Okay, so here's the sine of that angle. Now here, theta is stretched out along this x-axis. Okay, so as theta increases, we're just going further along the x-axis. The nice thing about polar coordinates is as theta increases, we're actually, theta is actually represented as an angle, a degree of rotation from that positive x-axis, or this what we call the polar axis now, okay? So now, right now, theta is at 0, and so here we see this green line pointing in the positive x-axis. That represents the direction of theta, okay? And this dotted line represents the opposite direction of theta. So if we had a negative radius, that's the way that that point would be graphed if we had a negative radius. Okay, so I have a slider down here and I can increase theta. So as theta increases, we see that our sine value is going to increase until we hit pi over 2, right? So remember though, sine of theta is going to be r, because that's our equation, r equals sine theta. So as theta increases, my radius is going to increase until we get to pi over 2. So let's do that. So notice, see my radius is increasing. This green point, its distance from the center there, that's the radius. So that is increasing until we get to pi over 2, where we have a radius of 1. Okay, so it increased until we had a radius of 1. Now it's going to decrease until we have a radius of 0, right? So this distance to this green point is our radius. That is going to decrease as theta increases until we get to pi radians, right? And then what happens? We retrace the circle, because as theta increases, now theta is still increasing, right? But now my radius is negative. So see that dotted line there? My radius is negative now. So that's why my point is tracing on the positive side over here. So we're tracing out that circle again. Okay. I guess another way to think of this is this green line segment will always be the same length as this green line segment from the origin to our green point. The radius here is the y value here, and vice versa. Okay, so I hope that makes sense why we get that circle now. And it traces it out twice, once for the positive hump of sine, and then once again for this negative hump of sine. Okay, so that's why we get that with sine. The cool thing about this app is we can type in any equation we want over here. Instead of theta, though, it's using t. Don't know why they chose t, but let's try cosine and see what happens. Okay, so there's our good old cosine graph. Now theta is at 0 and cosine is at positive 1. So here, notice our radius is already at positive 1. Okay, because cosine starts out at 1, this radius is going to start out at 1. And as I increase theta, this radius is going to decrease until we have a radius of 0 at pi over 2. So let's increase theta. My radius decreases until we get to pi over 2. And we have a radius of 0. Okay, and now I'm going to have a negative radius as theta increases till we get to 3 pi over 2. Okay, so, and then it's going to come back to 0, right? So now my theta is going to increase, but my radius goes into that negative dotted line territory. And then we get to pi, where we have that radius of 1, right, or negative 1, and that completes our circle. And then a second time around, as we complete one period of our cosine function. So yeah, one period of cosine and sine will trace their circle around 2 times. Okay, so that's why cosine gives you this circle over here, and sine gave you this circle that we graphed by hand up here. Okay, so please do have some fun with this. Log on to click on the link I just said is in the description below. Type in some equations here. See how the Cartesian graph relates to the polar graph, and have some fun with it. I hope it blows your mind and that you enjoy it. Okay, I will see you in the next video where we will learn some shortcuts, tips and tricks, ways that we can speed up this graphing process as we graph by hand. Okay, I'll see you there. Bye.